Ever wondered how some of the most critical applications, like, your favorite online database or maybe a massive distributed system, manage to keep their data perfectly consistent and
Yeah.
available even when they're running in a really dynamic environment like Kubernetes? It's a huge challenge, really. Today, we're doing a deep dive into a powerful Kubernetes resource that actually makes this possible, StatefulSets.
Exactly. And our mission today is really to unpack stateful sets. What are they? Why are they absolutely essential for certain kinds of applications? And, how do they actually work their magic behind the scenes? How do they bring that consistency and order to what can often feel like the chaotic world of distributed systems?
Yeah, Kubernetes can definitely feel like a maze sometimes, especially for beginners. And managing data just adds this whole other layer of complexity. But StatefulSet seems specifically designed to simplify this, right? To ensure those critical applications maintain their unique identity and, crucially, their data integrity. I like to think of it maybe like a highly organized team. Every member has their own specific ID, maybe a dedicated desk, their workspace that always stays with them. And they follow a very precise set of steps for everything they do, even if they get swapped out for a moment or moved around. Does that sound about right?
That's a great analogy, actually. It really captures the essence.
Okay, so let's unpack this then. What exactly is a stateful set, fundamentally, in the Kubernetes world?
So, at its core, a stateful set is a workload resource. It's specifically engineered to manage stateful applications. Now, the key difference compared to something like a standard deployment is how they treat pods. Deployments see pods as interchangeable, totally disposable, perfect for stateless stuff, but stateful sets. They make sure each pod has a unique identity and, critically, consistent, persistent storage that sticks with that identity. This is absolutely vital for apps that need to maintain state over time.
Okay, so it's about giving each pod a distinct personality almost. What are the key characteristics that define this personality? What makes them special?
Exactly. Personality is a good way to put it. So the first big one is stable network identity. Each pod managed by a stateful set gets a unique, predictable name. Think like DB0, DB1, and so on. And a stable host name, too. This isn't just for neatness, it allows for consistent addressing. Really important when components need to find and talk to specific instances, like in a database cluster, where nodes need to know exactly who's who.
Right, like a
Yeah.
primary needs to know its replicas reliably.
Precise.
And if they have that stable identity, what about their data? Does that stay with them too? Does that desk, in our analogy, follow them?
Absolutely. That leads right into the second key characteristic, persistent storage. Every single pod in a stateful set gets associated with its own dedicated persistent volume claim, or PVC. That's the magic piece that ensures its data persists across restarts, or even if the pod gets completely rescheduled onto a different node in the cluster. Your data is essentially glued to that pod's identity.
Okay, so the data isn't just floating around, it's really tied to that specific pod. Now, you also mentioned order. Does it matter how these pods start up or shut down?
Oh, it definitely does. For many stateful applications, it's critical, and that's the third characteristic. Ordered operations. Stateful sets ensure pods are created, updated, or even deleted in a very specific, predictable sequence. So DB0 will always be created and become ready before DB1 even starts. This is absolutely vital for applications needing sequential startup think, a primary database instance needing to be fully up before its replicas try to connect, or for careful scaling to maintain data integrity.
That's fascinating. So you mentioned earlier that stateful sets solve this challenge of maintaining state in a dynamic distributed environment. Can you give us some examples? Where do we actually see these stateful sets in action in the real world?
Oh, they're foundational in many places, absolutely indispensable for running databases like MySQL or PostgreSQL. Each pod there needs its own data storage and that stable network identity we just talked about for replication. They're also essential for managing distributed systems, think Apache Zookeeper or Elasticsearch. These inherently require unique pod identities and often very strict ordered startup sequences for their consensus algorithms. And even for things like deploying message queues, maybe Kafka, those pods rely heavily on consistent storage and predictable naming for coordination across the queue.
Wow, okay. So it sounds like they're absolutely critical for anything that needs to remember who it is and what data it holds. But it begs the question, why can't we just use standard Kubernetes deployments for everything? I mean, what unique requirements do these stateful applications have that make stateful sets so crucial? Why not just stick with deployments if we know them?
Well, the short answer is standard deployments just aren't built for it. They simply can't fully address those core requirements. Stable identities, persistent storage tied to a specific instance, and especially those ordered operations. Deployments are fantastic for stateless microservices, where any instance can handle any request. If one pod dies, you just spin up another identical one, no big deal. But try that with a database primary. That's a recipe for disaster, right? Data loss, inconsistency. Stateful sets provide the reliable, kind of opinionated management these applications need. They guarantee data consistency and operational stability in ways deployments just aren't designed for.
Okay, that makes sense. So let's break down the core reasons developers really lean on stateful sets. Beyond that fundamental difference, what are the key benefits driving their use?
Right. So first and foremost, that stable identity for pods, it's absolutely non-negotiable for consistent communication. Think about leader-follower replication in a database again. Followers need to consistently know who the leader is, and the leader needs to know its specific followers by name. Then there's the persistent data, like we discussed. Each pod gets its own dedicated storage via those PVCs, and that data survives. Pod restarts, failures, rescheduling the data sticks, that's fundamental. No data loss is the goal.
And the order. How critical is that in practice?
Extremely critical. That's the order, deployment, and scaling. This feature prevents a whole cascade of potential issues in applications that depend on sequential startup or shutdown. Imagine a database primary needing to fully initialize before replicas even attempt to connect. Stateful sets enforce that specific order, and this leads directly to reliability for stateful workloads. They reliably handle these complex applications databases, key value stores, ensuring consistent behavior even when things are changing in the cluster. And finally, honestly, simplified management. They automate so much. Pod naming, storage binding, ordered scaling. It dramatically reduces what would otherwise be incredibly tedious, error-prone manual work.
Okay, that really clarifies the why, but it also raises an important question. What's the real risk? What happens if you don't use stateful sets for these kinds of critical applications? What's the actual nightmare scenario?
The nightmare scenario involves a lot of manual babysitting and a very high risk of things going badly wrong, specifically data loss or inconsistency. Without stateful sets, you'd be trying to manually manage pod identities, figure out which storage volume belongs to which logical instance, ensure they start in the right sequence. It's incredibly error-prone, fragile, and it just doesn't scale. Using deployments, for example. You could easily lose data because there's no guarantee that a replacement pod gets the same storage, or you'd run into communication problems because pod names and IPs change constantly. This leads to application failures, weird inconsistencies, stuff that's incredibly hard to debug after the fact.
Oof, yeah, sounds messy. To really bring this home, let's use a concrete example. Imagine you're trying to run, say, a MongoDB cluster in Kubernetes. How would a stateful set help there?
Right, MongoDB is a perfect example. You'd absolutely use a stateful set. It ensures your MongoDB pods get those predictable names, maybe Mongo 0, Mongo 1, Mongo 2. It makes sure they start in the correct order, which is vital for establishing the replica set correctly. And crucially, each pod, Mongo 0, Mongo 1, Mongo 2, gets its own persistent storage volume. So here's the key part. If Mongo 1 crashes, the stateful set controller immediately steps in. It recreates a pod, makes sure it's called Mongo 1 again, and attaches the exact same stored volume back to it. This means the database maintains its consistency. You avoid data loss, you avoid disruption. It's the difference between having a robust, self-healing database cluster and one that's constantly falling over or losing data.
Okay, I'm sold on the what and the why.
Yeah.
For the really interesting part, the how do stateful sets actually pull this off behind the scenes? What's the fundamental workflow from definition to operation?
Yeah, the mechanics are quite elegant, actually. So at a high level, you define a stateful set using standard Kubernetes configuration files, usually YAML. Then, the stateful set controller works closely with the Kubernetes scheduler and other control plane components. Their combined job is to make sure your stateful application runs reliably, maintaining that crucial consistency throughout the pod's entire lifecycle, even as things change in the cluster.
All right, let's walk through that workflow step by step. First, you have to actually define one. What does that look like? What's in that YAML file?
Okay, so you start by defining a stateful set. The YAML definition includes a few key parts. There's a pod template, like in a deployment, specifying the container image, resource limits, ports, all that usual stuff. But critically, it also contains a volume claim template. This is super important. It's the blueprint for creating those unique, persistent volume claims for each pod. This tells Kubernetes, hey, for each pod you create, make sure it gets its own dedicated storage based on this template. You also specify the desired number of replicas and often reference a service name, which we'll touch on, for networking. So for example, for a MySQL database, you define the MySQL container image, a PVC template requesting storage for its varlib MySQL data directory, and maybe set replicas. 3, Kubernetes will then aim to create MySQL 0, MySQL 1, and MySQL 2.
Got it. So you define the template for the pod at its storage. Once that's applied to Kubernetes, what happens next? How do the pods actually get created? Is it just all at once?
No, definitely not all at once. That's where the order comes in. The next step is ordered pod creation. The StatefulSet controller is very deliberate. It creates the pods in a strict sequential order based on their ordinal index. It starts with pod 0. It waits for pod 0 to be fully running and ready before it even starts creating pod 1. Then it waits for pod 1 to be ready before starting pod 2, and so on. Each pod automatically gets its unique, predictable name. The StatefulSet name plus that index, like MySQL0. So, in our MySQL example, MySQL0 is created first. The controller waits until it's healthy. Only then does it create MySQL1. This careful process helps ensure things like database replication can be set up correctly from the very beginning.
Okay, the order makes sense. And as each pod is created, the storage gets tied to it somehow. How does that actual binding happen?
Exactly. That's the persistent storage binding step. As each pod, say MySQL 0, is created, the controller also creates a unique persistent volume claim specifically for it, using that volume claim template we defined earlier. This PVC then gets bound to an actual persistent volume, PV, available in the cluster, maybe a disk on your cloud provider. This ensures that the pod's data directory, like varlib MySQL for MySQL 0, is backed by persistent storage. And crucially, that specific PVC remains uniquely tied to that pod's identity. MySQL 0, even if the pod itself gets deleted and recreated or moved to a different node, it will always try to reattach to that same PVC.
Ah, so the identity and storage are really locked together. Now, what about that stable network identity you mentioned? How do other services or pods find MySQL reliably no matter where his pod might be running?
Good question. That's handled by the stable network identity mechanism. Each pod gets a predictable, stable host name. It usually follows a pattern like podname.service-name.namespace.svc.cluster.local. So maybe mysql.mysql-service.default.svc.cluster.local. This is often achieved by associating the stateful set with what's called a headless service. Unlike a regular service that load balances requests across pods, a headless service doesn't have its own IP address. Instead, when you query its DNS name, it directly returns the individual IP addresses of all the pods managed by the stateful set, MySQL 0, MySQL 1, etc. This stable host name is absolutely crucial for stateful coordination. Think back to MongoDB. Mongo 1 needs a reliable way to find and connect to Mongo 0 to set up replication. That stable host name makes it possible.
Okay, headless service provides the stable names. Now, speaking of dynamic environments, how does a stateful set handle things like scaling up or down, or rolling out updates? It seems like a really tricky moment for stateful apps where consistency could break.
You're right. Those are critical moments, and it's actually one of the biggest advantages of stateful sets. They handle scaling and updates with that same ordered precision. When scaling up, say, from 3 replicas to 4, the new pod, MySQL 3 in our example, is created only after the previous highest index pod, MySQL day 2, is fully ready. Scaling down is done in reverse order. If you scale from 3 down to 2, MySQL 2 is terminated first, then MySQL-1 if needed. This orderly shutdown can be important for gracefully removing nodes from a cluster. Updates, like changing the container image version, are also rolled out sequentially, usually from the highest index down, though this can be configured. So MySQL 2 would be updated first. The controller waits for it to be ready and stable before moving on to update MySQL 1, and so on. This prevents destabilizing the entire application during an update.
Wow, that ordered approach applies to everything. Okay, and finally, the inevitable question. What about failures? If a node dies or a pod just crashes, what does the stateful set do to recover?
That's where stateful sets really shine, providing failure recovery. If a pod fails, maybe the node it's on crashes, the stateful set controller detects this. It automatically works to recreate that specific pod. But here's the magic. It recreates it with the exact same name, for example, MySQL 1, ensures it reattaches the exact same persistent volume claim containing its data, and reestablishes its same stable network identity. So if MySQL 1 crashes, the stateful set brings MySQL 1 back to life, ensuring it has its original storage and hostname. This preserves its role and data within the database cluster, making the application remarkably self-healing while maintaining that crucial state. If you step back and look at the bigger picture, this entire workflow is about automating these incredibly complex operational tasks for stateful applications. Tasks that historically were manual, extremely error-prone, and required deep, deep expertise for every single hiccup or failure. It fundamentally changes how we manage these critical systems.
That really is a powerful transformation. Okay, so just to quickly recap, what are the absolute key components working together behind the scenes to make all this ordered, stateful magic happen?
Sure. You've got the pod template, which defines what the application container looks like. Then, super important, the volume claim template, which dictates how that dedicated persistent storage is created for each pod. You need the service name, which usually points to that headless service to provide the stable individual network identities. And of course, the underlying controller logic that enforces those ordered operations for everything. Creation, scaling, updates, deletion. These pieces work together seamlessly to deliver that robust, stateful management.
So wrapping this up, what does this all mean for you, the listener? We've really unpacked how stateful sets in Kubernetes are absolutely critical. They're essential for managing applications that need to maintain state databases, distributed systems, you name it. They bring order to what could easily be chaos in a dynamic cloud environment.
Yeah, absolutely. They provide those three pillars: stable identities, persistent storage, and ordered operations. These directly address the core challenges of reliability and consistency for stateful workloads. Honestly, understanding them is pretty foundational for building truly robust, scalable applications today. You're likely interacting with systems managed by stateful sets every single day without even realizing it.
It really is a powerful concept, and it simplifies something that, if you had to do it manually, would be incredibly complex and fragile. Knowing about stateful sets lets you appreciate those hidden layers of stability and predictability that are working behind the scenes in so many services we rely on.
Definitely. And maybe here's a final thought to leave you with. We've talked a lot about databases and similar systems, but considering how essential data consistency and uptime are for almost every modern application, how might these core principles we see in stateful sets, stable identity, persistent state, ordered operations, apply more broadly? Think beyond just databases. What other stateful interactions do you rely on daily? Maybe your online banking session, your social media feed's consistency, even collaborating on a document in real time. Where else is that consistent identity, and maybe even a specific order of operations unknowingly critical to making things work smoothly for you?